This is a video about the positioning of spray nozzles in gas scrubbing applications for optimal results. Now, the general idea in a gas scrubber is to get as much surface area of fluid in contact with the gas as possible. And one of the ways we do this with nozzles is to atomize the spray to reduce the drop size. This increases the surface area of the spray. And the other function of the nozzle is to distribute that spray over the gas flow. When we're spraying a nozzle into a gas flow, we can calculate what we call the circle of wetting of any nozzle. If you imagine looking face onto the nozzle, we'll have a spray angle and it will produce a circular spray pattern face on. This can be varied depending on the spray angle of the nozzle. What we find is when spraying into gas flows, we can quite easily model where the heavier droplets will go using simple trajectory software. In using this software, we can work out what that overall spray pattern is going to be in an idealized gas flow. And by an idealized gas flow, we mean a laminar gas flow of a set velocity. We can quite easily calculate this circle of wetting for any given nozzle spraying at any given pressure if we know the drop size from that nozzle. Once this is calculated, then it's a question of mapping those circles onto the overall geometry of the gas flow, the geometry of the chamber. So we're getting a nice even coverage of spray over the entire gas flow. Now, it's never going to be entirely possible to give completely even coverage, because if you imagine we've got, say, a circular scrubbing chamber and then we're mapping various circles of wetting from the different nozzles onto that, we're never going to get completely even coverage. We're going to have some overlap, especially around the edges, but we get it as even as possible, and then that's going to give us an idealized scenario, an idealized spray coverage that's going to give us some optimal results. There's a couple of problems here. We also want to get the drop size as small as possible, but as we start to reduce the drop size and get smaller and smaller droplets, we also reduce the circle of wetting produced from any given nozzle. And this is particularly true in fast-moving gas flows. As we reduce that drop size down, they get entrained faster and faster within the actual gas flow itself. And so the distance they can actually penetrate perpendicular to the gas flow gets smaller and smaller. So the circles of wetting get smaller and smaller. So in order to achieve complete coverage with very small nozzles and small drop sizes, we need more and more of them. And this is not always practical. We end up with lots of complicated pipe work within these gas scrubbers, and it's just not possible to have hundreds of small misting nozzles all over the gas flow. So there's a tension here, and a balance needs to be found between what practical number of nozzles that we can insert into the gas flow and the idealized drop size. Once we've established how many nozzles we can actually get away with using at what drop size, we can then map those around the gas chamber and hopefully end up with a good scrubber design. However, that idealized mapping of circles over the overall gas flow may not always be ideal. Remember, one of the assumptions we're using when calculating that circle of wetting is an idealized gas flow, a laminar gas flow going all in one direction. And that simply ain't the case in most gas scrubbers. We've got different areas of different temperature, we've got different areas of different gas flow, we've got turbulent gas flow, we've got spray nozzles spraying into each other and interacting. So often the idealized completely even distribution of spray isn't actually ideal. And the only way we can actually work out whether that's the case or not, or whether we need to have differential areas of spray to compensate for, say, a fast-moving area of the gas flow, the only way we can calculate that is through computational fluid dynamics. So sometimes that ideal scenario may not be ideal, but we won't know until we've done the CFD on that. One other consideration to think about when positioning spray nozzles is whether to spray them counter current or in line with the current of the gas flow. So you can see on this diagram here, this is showing the spray trajectory for the heavier droplets on the same nozzle spraying at the same pressure in the same gas flow, but the orientation of the nozzles is different. In one, we're spraying in line with the gas flow, and in the other, we're spraying counter current to the gas flow. So you can see on the counter current gas flow, it actually gets a wider distribution. So we have a wider circle of wetting when we change the orientation of the nozzles. This can also be helpful when positioning spray nozzles. One final thing to consider in positioning is the wetting of the walls. Now, in scrubbers with lots and lots of nozzles in them, we're going to inevitably end up with some of the spray on the walls, and this is a waste, because as soon as the spray hits the walls, we're destroying all of that lovely drop size, atomization, we're removing all of that surface area, and so we're kind of wasting some spray there. When considering large scrubbers with an array of nozzles around the wall and many in the center, what we may want to do is angle those ones around the wall into the gas flow a bit, so they're not spraying straight down or straight up, they're spraying at an angle, and so we're reducing the amount of liquid fluid that's actually hitting the walls. Another nifty solution that we've done in the past is design special half cone nozzles, half cone spiral nozzles, and these produce like a semicircle of spray rather than a circle of spray. We put these ones around the edge, and so we're getting less water on the walls, and so getting more of that spray into the actual gas flow so it can do its thing. And finally, underpinning all of this is the main restriction on how many nozzles we can use. We've got to consider maintenance and the retraction of those nozzles for maintenance. In an ideal scenario where these things weren't in play, we'd have maybe hundreds of nozzles all over the gas flow producing nice fine sprays, but that just isn't practical. We've got to consider how we're going to get the nozzles in, how we're going to get them out, how we're going to maintain them. So we're going to need the suitable lances and positioning lances to actually get these nozzles in place. That can have a really, really big influence on the number of nozzles that we can actually use, and so the overall scrubber design. Overall, positioning is a balance between the practical considerations of getting nozzles in position and having practical amounts of pipe work and infrastructure in place to position them, and the idealized spray scenario. It's a balance between those two forces. Good news is we're used to giving advice on how to make that balance, how to keep it practical and still highly functional. We can manufacture all of the lances and retractable lances, all of those positioning systems, and we advise on these gas scrubber design and ideal nozzle positioning for engineering companies all over the world. So you're in safe hands with the spray nozzle people when it comes to advice on nozzle positioning for gas scrubbers.